So today we're talking about the three main ways machines learn. It's a huge topic, right? But it's not magic, it's a science. And understanding these three core methods is key to understanding the AI that's shaping our world. Let's dive in.
And that really is the central question, isn't it? How does a machine actually learn? Because it's not just about memorizing a bunch of facts. It's about something much deeper. It's about being able to generalize from experience, to find patterns in the messy data of the world so it can make smart predictions about stuff it has never, ever seen before. So how does that even work?
Okay, so at its absolute core, machine learning is really just one thing: pattern recognition. But on a massive, almost unimaginable scale. The basic idea is you give a computer a mountain of data, and its job is to learn, to see the hidden relationships, the secret structure inside that data. Why? So it can make really good guesses about brand new data it's never encountered.
All right, let's make this way less abstract. Imagine for a second that you're the machine, and you're looking at this table of housing data from Portland. Pretty simple, right? You've got the size of a house in square feet, and you've got its price. Your entire job is to find the pattern here. Is there a relationship between how big a house is and what it costs? This right here is the raw material for learning.
Okay, so let's get into method number one. This is probably the one you've heard of the most. It's called supervised learning. And honestly, the best way to think about it is, well, it's like learning with a teacher, a really, really patient teacher who kind of gives you all the answers ahead of time. Think about it like you're studying with flashcards. It's exactly the same idea. On one side of the card, you've got the question, like in our housing example, what's the living area? And on the other side, you've got the correct answer. Here's the price. The machine just goes through thousands, maybe millions of these question and answer pairs. In the biz, we call this labeled data. Now, with this teacher, there are really two main types of problems or questions it can pose. If the answer you're looking for is a number, like a price, that's called a regression problem. But if the answer is a category, like is this email spam or not spam, that's a classification problem. So one is about predicting a value on a spectrum, and the other is about picking a specific label. It just depends on what kind of answer you're after.
And the whole reason for looking at all those flashcards? It's to learn the secret connection, the relationship between the questions and the answers. The goal is to build a model, a kind of hypothesis about how the world works so that it can look at a brand new house, one it's never seen, and accurately predict its price just based on the square footage. That's the magic trick.
Okay, but what happens when you don't have a teacher? What if there's no answer key? Well, that brings us to our second method, unsupervised learning. And this is where the machine is really, truly left to figure things out on its own.
And the analogy for this one is perfect. Picture this. You're a detective. Someone just drops a huge box of evidence on your desk. It's completely unsorted, no labels, no notes, no help whatsoever. And your job is to find the connections, to group the things that seem to belong together, to find the hidden patterns, all by yourself. That is exactly what an unsupervised algorithm is trying to do with data.
Which kind of begs the question, right? How on earth does that even work? If there are no right or wrong answers to learn from, where does the machine even begin? Well, let's take a look at one of the most famous ways to do it. So a really popular method is called k-means clustering. It's actually a pretty elegant, simple repeating process. Here's how it starts. First, the algorithm just looks at all our unlabeled data points, and then it makes a completely random guess. It just drops a few cluster centers onto the map. These are its first, probably wrong, guess for the middle of each group. And then the loop begins.
Okay, step one of the loop is the assign step. And the rule is super simple. Every single data point looks around, finds the closest cluster center, and joins its team, at least for now. You can think of it like everyone in a big room just walking to the table that's nearest to them.
Next up is the update step. And this is where it gets really clever. Each of those cluster centers now looks at all the data points that just joined its group, and it calculates their average position. Then it moves itself right to that new spot. It's basically finding the new center of gravity for its little group.
And that's it. It just repeats those two steps over and over and over. Assign and then update. Assign, update. And with every single cycle, the groups get a little tighter, a little more accurate. Eventually, the centers stop moving around because they finally settled into the best possible spots. They found the most stable groups, revealing the hidden structure in the data. And the amazing part? It did it all without a single label to guide it.
All right, so we've covered learning with a teacher, and we've covered learning all by yourself. That brings us to our third and final method, which is all about learning from trial and error. It's about learning through direct experience, and it's called reinforcement learning.
The core idea here is super intuitive. It's learning from consequences. The best analogy is a toddler learning to walk. It's not reading a book, it's just trying things. So you have an agent, think of it like this little robot here. It exists in an environment. It tries an action, and then it gets feedback. Did that action work out? Did it fall over? Or did it stay balanced? Was that outcome good, or was it bad?
So, if we want to get just a little more formal, there are 4 key players in this game. You've got the agent, that's our learner, our robot. You've got the environment, which is just the world it operates in. There's an action, which is any move the agent can make. And finally, there's the reward. That's the feedback, positive or negative, that it gets from the environment. It's just a constant loop. Action, reward, action, reward.
But here's the crucial part. The goal isn't just to get the biggest reward right now. The agent is trying to learn a policy, which is basically just a long-term strategy. And the goal of that policy is to maximize its total, cumulative reward over a long period of time. It's learning how to play the long game, not just going for the quick and easy points.
So there you have it. 3 really different ways that machines can learn. But the real cutting edge, where things are getting wild in AI today, is what happens when you start combining these methods.
Just think about it for a second. We have learning with a teacher, learning alone, and learning by doing. Each one is powerful on its own. But what happens when you combined all 3 of them at a massive, massive scale? What if you could train one single, gigantic model on just an unbelievable amount of data? Well, that's what's happening, and it's leading to a whole new way of thinking. This new paradigm is what we call foundation models. This is the big idea behind the massive models you hear about, like GPT. The concept is a game changer. You stop building a new, special model for every single little problem. Instead, you pour all your resources into pre-training one enormous general-purpose model on a ridiculously huge and varied dataset.
It's kind of a 2-step process. First, there's the pre-training phase. This is where the model spends a ton of time and computer power just learning general patterns from all that data. A lot of this is unsupervised, just finding structure in, basically the entire internet. Then comes phase 2, adaptation. You take this powerful, pre-trained brain and you show it just a tiny handful of examples for a specific new task. And because it's already learned so much, it can adapt and solve that new problem with amazing efficiency.
What this all really represents is a monumental shift in strategy. We're moving away from the old world of painstakingly building thousands of different specialist models from scratch. Instead, the new approach is to build one incredibly capable generalist model and then just adapt it for everything else. It's a huge, huge leap forward in both efficiency and raw power.
And that brings us to the big final question to think about. We've seen how machines can learn with a teacher, how they learn by themselves, and how they learn through experience. And now, we're seeing them combine all of these methods at a scale that's honestly hard to even wrap your head around. So as these machines continue to master every way of learning, you have to wonder, what are they going to end up teaching us?